From Star Wars in the 1970s to the newest Avatar movie, us humans, we seem to have been fascinated with finding aliens for decades and counting. With designated missions like Kepler and Plato, astronomers look for habitable exoplanets every day. Yet what if life exists in the most inhabitable, most darkest, and mysterious places in the universe? How is this possible? Let me explain. When we imagine life, we imagine water, and perhaps sunlight. But this is because we're all most familiar with photosynthesis. Photosynthesis, however, as we all know, requires sunlight and water, which may not be available on most planets. Chemosynthesis, on the other hand, is an alternative path to energy, where certain chemical reactions lead to the energy required for life. Organisms who perform chemosynthesis instead of photosynthesis are called chemoautotrophs, or the general domain of archaea. The most common and simple chemosynthetic reaction is this reaction of carbon dioxide plus molecular hydrogen creating methane, water, and energy. Organisms who perform this reaction for living are called methanogens, as they generate methane in their energy production. These methanogens are particularly interesting in looking for life on exoplanets, as planets commonly have carbon dioxide plus H2 in their atmospheres. But just how do we study these single-celled chemoautotrophs before looking for them on other planets? Well, we just gotta look in our own ponds first. This is a depiction of a hydrothermal vent at the seafloor spreading zone, or mid-ocean ridge. The oceanic crust in this area has cracks through which the seawater seeps in through the crust. As the water gets deep enough, it gets superheated and comes in contact with all the juicy minerals and compounds molted in the crust. As the water continues to move through the crust, it cools down even more and jets out through any weak spots in the crust, called smokers. The result of these hydrothermal vents is the release of all the important chemicals required for chemosynthesis that include all the minerals over here, as well as H2S and H2, which are treats to chemoautotrophs. Life can take form anywhere. And now we know that the existence of plate tectonics can support some type of life. A living example of this lurks in our own neighborhood at Saturn's largest moon, Titan. Titan is the only other object in our solar system to have liquid bodies like oceans, rivers, and lakes, along with a very, very thick atmosphere. However, these oceans are made of liquid methane and ethane, and temperatures are frigidly low, around 94K. Yet, there's a very high possibility that Titan, a toxic and cold methane world, hosts archaic life. If we hypothesize that such life exists on Titan, then we would expect a methane-based chemistry, where we would see methane reacting with hydrogen gas to form other hydrocarbons. This would mean that we would see strong evidence for intake of hydrogen gas from the moon's atmosphere. And guess what? The Cassini-Huygens probe that flew right through the Titan's atmosphere found exactly such measurements. The graph of the atmospheric composition of Titan along with different altitude shows that there's a clear and mysterious intake of hydrogen gas from the atmosphere at lower altitudes that cannot be explained besides anything but chemosynthesis. So, does this mean we can find Titanians before Martians? We'll have to wait and see until a probe actually lands on Titan.